Okay. All right, so we left off talking about moles and how we can relate the masses found on the periodic table to the atoms of a molecule, or the atoms or molecules of an element or compound, and to the grams of that thing. So we're going to continue our discussion about that, and then we're going to do a little worksheet to help us practice these types of conversions. Okay? So here they're asking us to calculate the number of moles of sulfur represented by 1.8 times 10 to the 24th atoms. So we're starting with atoms. We're going to go to moles. So I'm going to set it up. 1.81 times 10 to the 24th atoms. Okay, and I'm going to convert that to moles from the atoms, just in this way. Okay, and the number that I always associate with moles is what? Okay, there's 6.022 times 10 to the 23rd atoms in 1 mole. So moles, I'm always going to use the number 1 when it's a conversion like this. Okay, when it's ever with something other than moles itself, it's always going to be 1, because it's 1 mole for every, what number do I put here? 6.022. That's how many atoms, right? The atoms cancel. I'm left with moles. So this times 1 divided by 6.022 times 10 to the 23rd. That's how I'm going to carry out that calculation. Okay? And if we do the calculation, it comes out to be 3 moles of sulfur. Okay? Now, what is the mass in grams of 3.01 moles of sulfur? So now they're taking it a step further. They're saying, we figured out how many moles there are in this many atoms. Now can we take that many moles and can we convert it to grams? Okay? So the way that we're going to do that is by using this conversion factor. 1 mole of sulfur equals 32.06 grams. We see that right here. Okay? That's where we get that information. So I wouldn't give you this because you would look there to find it. Okay? So obviously I have these two ratios. I'm going to take my 3.01 moles of sulfur, and I want to convert it to the grams of sulfur from the moles of sulfur. So my moles of sulfur are going to cancel. I'm left with grams. Okay? So what number goes on top? 32.06 grams of sulfur for every 1 mole of sulfur. So I would take 3.01, multiply it by 32.06, and I would get 96.5 grams of sulfur. Okay? Because it would get set up in this fashion. So this times this divided by this, but it's just 1, so I don't have to do that. Okay, and here they're telling us that this is often a 2-step process, but you honestly don't have to do it in a 2-step process. We could have started, so they had us go through this in 2 steps. They had us start with the atoms of sulfur, and they went to the moles and then to the grams. But what if we wanted to just go from atoms straight to grams? Could we do that? Yes. I could still start with 1.81 times 10 to the 24th atoms and skip the middle guy. What do I want to get to? Grams from the atoms. Well, how many grams are in how many atoms? What number can I use for the atoms on the bottom? I'm still going to use 6.022 times 10 to the 23rd. If I have 6.022 times 10 to the 23rd atoms, how many grams of sulfur is that? 32.06. So, okay, we can do this, and it'll equal the same as what we found here, 96.5. This is going to be 96.5 grams of sulfur. My atoms canceled. I'm left with my grams. Okay? So don't think that you have to do it in that two-step process. If that makes sense to you to do that way, then do it. Excuse me. Then do it that way. But you don't need to. You can always set it up like this as well. Okay? Straight from the atoms to the grams. Okay. So let's practice a few here. Let's just set them up. Calculate the number of atoms in 1.7 moles of boron. So I'm going to start with my 1.7 moles because that's what they gave me. And I'm going to convert it to what? Atoms. From the moles on the bottom. So the moles will cancel, and I will be left with atoms. What number do I put on top? What number is on the bottom? 1. Okay, 2.5 moles of sodium. Excuse me. And I want to go find the mass in grams. So what do I put on top? What unit do I put on top? Grams. What unit do I put on the bottom? Moles, because the moles will cancel. So what number do I put on top? What number do I put on the bottom? 1. Excuse me. So for moles, I use the number 1. For mass, grams, I go here. For atoms, I use the number 6.022 times 10 to the 23rd. Now, not only atoms, but molecules, or atoms, or particles, something that's really, really, really tiny, that you need a whole lot of, you're going to use that number. Okay? 5.0 grams of Al. And I want to convert that to what? Atoms. So I'm going to, what unit am I going to put on the top of this conversion? Atoms. What unit goes on the bottom? Grams. What number goes with atoms on the top? What unit goes on, or what number goes on the bottom? .98 grams. Okay? So I have to find that from my periodic table. That's it. That's what I'm doing. Making sure first that I'm setting it up correctly, and then once I have done that, it tells me what to put here. Atoms, I know what number to use. Grams, well, it's the grams of Al, so I have to use this number. Okay? This is how I'm going to perform these simple conversions. So the mass of gold, so I have 5 times 10 to the 6th atoms. And I want to convert that to grams. Mass is always in gram units, okay? Unless they specify they want kilograms. So if they don't tell you, then just go to the grams, okay? Calculate the mass of 5 million atoms of gold. So what unit goes on top? Grams. What unit goes on the bottom? My atoms cancel. Okay. What number goes on the top? What number goes on the bottom? Okay? That's how easy it is. That's how I do these conversions. Okay? I just simply set them up in this fashion. Okay, now this is just showing you how to go back and forth. What you've learned already is way easier than trying to figure out this. Okay? So don't try to figure that out. Okay? We'll come back to that. So H2 plus O2 produces H2O. So I balance it, I put the 2 there, I put a 2 there. This is represented as 1, a coefficient of 1. This is a conversion factor. 1 O2 equals 2 H2Os. That's a conversion factor. But is this in grams? Is it 1 gram of oxygen equals 2 grams of water? Is that what those numbers represent? No, that doesn't make any sense, right? Not at all. That's not what it represents. It represents the number of molecules or moles. The moles. 1 mole of O2 equals 2 moles of H2O. Okay? That's how this chemical equation works, through moles. So it's a conversion factor. So that means if I want to convert from one thing to another thing, I have to use a balanced chemical equation to do it. This is my conversion factor, 1O2 for 2 H2Os. So if I'm going to go from the moles of O2 to the moles of H2O, I have to do it through this conversion factor. How many moles of O2? 1. How many moles of H2O? 2. Okay? So, but did they start me out in moles on this question? Did they tell me how many moles of oxygen I had? No, they didn't. What did they tell me? How many grams of oxygen? So that means before I can actually do this conversion, what do I have to do first to the to the grams of oxygen? Convert it to moles of oxygen. That's the first thing. So I start with my 15 grams of O2, and I'm going to convert it to the moles of O2. Now that I'm in the moles of O2, look what I can do. I can go from the moles of O2 to the moles of H2O. Okay? So that's when I can do that step. What does the answer want? Do they want moles of H2O? They want the grams of H2O. They don't want the moles of H2O. They want the grams of H2O. So what do? Can I get the grams of H2O now that I have the moles of H2O? Can I do it? Yeah, absolutely. Grams of H2O from the moles of H2O. That's how I would do that process. Okay? What unit goes right here? Grams of oxygen. What unit goes right here? Moles of oxygen. What unit goes right here? Moles of H2O. I simply drop whatever came before, right? Because they have to cancel. And what am I left with? The grams of H2O. Okay? I didn't even put any numbers in there, but I have it set up correctly. But now that it's set up correctly, I can find all the numbers I need. What number do I put here for moles? Whenever grams and moles are together, moles are always 1. Grams, what is it? It's 32, not 16. It's 32 because it's 2 oxygens, right? 32 grams of O2. Where did I find this relationship? The moles of O2 to the moles of H2O. That's that ratio, right? So 2 moles of H2O for every 1 mole of O2. What number goes here on the bottom? Whenever grams and moles are together, moles are always 1. I already did the 2 for the H2O right here. That's where that comes into play. But here, this conversion, 1 mole of H2O has how many grams? Well, now I have to figure out the mass of H2O. Oxygen, 16, 2 hydrogens, that's 18. 18 grams of H2O. Okay? See what I did? I went from 15 grams. I know if I react 15 grams of oxygen with an excess amount of hydrogen, more hydrogen than could ever react with 15 grams of oxygen, it will produce whatever this is, whatever this comes out to be. Now, how would I perform this calculation? 15, and I would multiply everything across the top. 15 times 2 times 18 divided by 32. That's how I'd work that out. Okay? So, from 15 grams of oxygen, how many grams of water do you produce? That's how much? Okay. That's how much water I'm going to produce. Okay? All right. Now, don't worry too much about that. We're going to do that a whole bunch. A whole bunch. So this wasn't your one chance to figure that out. Okay? We're going to come back to this. That's called stoichiometry. Okay? And we're not quite there, but we're going to get there. Okay, now let's talk a little bit about chemical formulas, formula masses, and molar masses. We did a little bit of this just now on this sheet, okay? So the chemical formula is a combination of symbols that make up the compound, right? You have your elements and the amount of them, and that becomes your chemical formula. A formula unit is how we write ionic compounds. Ionic compounds are written in their lowest ratio formula unit, or in their empirical formulas, because that's their lowest ratio formula. And we say that's a formula unit. So if you ever see a formula unit, don't abbreviate it. Okay? It doesn't look good on your paper when you abbreviate formula unit. Okay? So it's in its lowest ratio formula. Okay? You guys are just getting it. Okay. Okay, it's coming through. It's coming through. All right. So, these are some chemical formulas here. H2, H2O. Sodium chloride would be a formula unit, okay? Because it's an ionic compound, and this is its lowest ratio formula unit. Okay? Calcium hydroxide, same thing. Okay? It's in its formula units. So here we have some more chemical formulas. Ammonium sulfate, 2 ammonium ions, 1 sulfate ion. So the brackets, what is it representing, right? It's representing NH4 and another NH4, and those two things are bonded to one SO4. Okay? So that's why I have this brackets 2 NH4s. These guys stay together, and I have 2 of them, and I have 1 SO4. Okay? This is a hydrate. Hydrates are multiplied by water, meaning it's because the water gets trapped in the salt crystals, and there's an exact number. Sometimes it's 2 water molecules, sometimes it's 3, sometimes it's 7. Here it's 5. This copper sulfate will have 5 water molecules trapped inside of its crystalline structure for every copper and 1 sulfate. There will be 5 water molecules trapped there in that ratio. Okay? So if I'm going to figure out the formula, the mass of this, I have to do it considering the water molecules as well. Okay, so I could find the mass of copper sulfate, and then I could find the mass of 5 waters and put them together. That would be the mass of this entire copper sulfate pentahydrate. That's what they would call it. Okay, here's some examples of some hydrates. This is the hydrated form with the 5 waters. You evaporate those off. You heat it up, evaporate the waters off, and it goes white. And so a lot of hydrates are very colorful. They'll have these cool green, blue, orange colors to them. And then you heat them up, and those colors go white. You guys are going to do a lab about that if you're taking the lab right now. We're going to do a hydrate lab where we heat up the hydrates. They're all colorful, and they go, colorless, so forth. Okay, so the mass, to find the formula mass, you simply need to add everything together. So here I have 2 hydrogens. Each hydrogen has a mass of 1.008, or 1, let's say. So that's added to a mass of 16 for the oxygen, and you get 18.02 grams per mole, or atomic mass units if you're talking about a single molecule. Okay, so the molar mass of H2O is 18.02 grams per mole, same as its atomic mass. Okay. So here, once again, this is ionic. So we would talk about it in formula units. What's the formula unit mass of ammonium phosphate? So we have 3. So here, let me break it up over here on the side. So NH4, and there's 3 of them, phosphate, PO4. Okay. So N, H, P, and O. This gets factored in. Okay. So I have 3 nitrogens. I have 12 hydrogens. I have 1 phosphorus and 4 oxygens. And that's what I would find the masses from. Okay. So this would be nitrogen 14 times 3, 12 times 1 for hydrogen. Phosphorus is 31, and 16 times 4 for the oxygen. And then you add it all together. Okay, and you would find the mass to be 149.10 grams per mole for ammonium phosphate. Okay, and that's how I would find these masses of these salts. These salts, not these. They're not molecules because they're not covalent. Okay. Okay. So carbon has a molar mass of 12.01 grams. So 1 mole of carbon has 6.022 times 10 to the 23rd atoms, which would have a mass of 12.01 grams. 1 mole of any element has that mass, and we've already kind of figured that out from what we've been doing. Okay. Now, the chemical equation. How is the chemical equation set up? Well, the chemical equation is set up to show reactants and products. These are your reactants. They're going to form this. Okay? So, we identify products and reactants. We use the chemical symbols. The reactants are written to the left of the reaction arrow. Products are written to the right. Sometimes you'll see little symbols that show, in this case, that one would show heat is necessary for this reaction, and the equation must be balanced. Okay, so here's a big, busy slide. Okay, but here we have our reactants. These are our reactants, right? These are our products in yellow here. Okay. This delta H right here is representing the heat energy that was required to carry this reaction forward. So sometimes you'll show that. We have to decompose the mercury oxide, so we have to add heat to do that. The physical states are also shown. What physical state is the mercury oxide in? Solid. What physical state is the mercury in after it reacts and decomposes? It's a liquid. That's what the L stands for. And the O2 becomes a gas. There's another one you would see called aqueous. Aqueous is when something is dissolved into water. Okay, so like sodium chloride, if you put it into water, so this is a liquid, this is a solid, okay, it would dissolve and it would become Na plus aqueous plus Cl minus aqueous. It would dissolve it. It would break apart, okay? So you can see that as well. So the chemical equation always represents, this is your starting material, this is what it becomes. So there's always a chemical change that's occurring. And that's what the chemical reaction is trying to help us see, that chemical change that would be taking place. So how do we know when a reaction has occurred? Well, there's a few ways, and this is another lab you guys are going to do. You're going to carry out a bunch of chemical reactions, and you're going to identify what type of reaction it was based on what's happening, and you're going to notice that there's a chemical reaction occurring because of things like gases being released. How do you know when a gas is being released in a chemical reaction? It starts to bubble. So when you see those bubbles, you know a gas was created. That means something has changed. Okay? A precipitate forms, a solid product. So you pour two clear liquids together, and all of a sudden, boom, you see this solid, like almost grain coming out. That's the precipitate. That's the solid thing that no longer will dissolve in the water. Okay? Water will no longer dissolve it, so it forms a solid product and comes out. Heat is produced, so you're holding the reaction, and it gets hot. That's an indication that a chemical reaction is occurring. Or it gets cold. That's another indication, okay, that it's occurring. If it's getting cold, that means it's absorbing heat from the solution around it. If it's getting hot, it's releasing heat to the solution around it. Sometimes you'll see a color change. Color changes aren't always necessarily a chemical reaction. They could also be physical changes, okay, at times as well. So other indications, maybe light is absorbed or emitted. You can measure that through a spectrophotometer, perhaps. Maybe the electrical or magnetic fields before and after the reaction change. Electrical properties might change. So iron can conduct electricity, but you react it with oxygen, becomes iron oxide. It no longer conducts electricity, right? So that would be a change in its electrical conductivity. So these are a few types of reactions that you would be able to identify. Combination, decomposition, single replacement, and double replacement reactions. Okay? Combination, you could kind of get the idea A plus B is going to form AB, right? Decomposition is exactly the opposite. You take AB and you decompose it into A plus B, like H2 plus O2 forming H2O. That is a combination reaction, or you take H2O and you decompose it into H2 plus O2. Okay? That would be decomposition. Single replacement. Single replacement and double replacement occur with ionic compounds, things that are ionic. Okay? So for this to happen, I need a single replacement. For that to happen, I need a metal like copper. And I need a metal that is in an ionic compound, like silver chloride. Or not silver chloride, let's say silver nitrate. Silver nitrate, okay? And the copper replaces the silver. So you get silver comes out, and the copper dissolves with the nitrate. So it replaces it. It's a single replacement, okay? And it's one metal replacing the other one. A double replacement is where you, instead of starting out with a metal that's solid metal, you start out with two dissolved metals. So something like silver nitrate again and sodium chloride. So I have silver and sodium metals, right? And I have nitrate and chlorine anions. So these are two ionic compounds. And the two metals, once again, just basically switch places. So this is double replacement. So the two metals switch places, and I get sodium nitrate and silver chloride. Those are my two products from a double replacement because they're switching places. Okay, and we're going to look at these. So here, once again, we have A plus B forms AB, combination reaction, right? Sodium plus chlorine, sodium chloride. It's a combination reaction. Magnesium oxide plus carbon dioxide. These two things come together and they form magnesium carbonate. Combination reaction. Okay? So here's some more examples. We don't need to spend time on that. Decomposition. We have AB decomposes into A plus B. Once again, the mercury oxide decomposing into mercury plus oxygen. Calcium carbonate decomposing into calcium oxide plus carbon dioxide. Okay? And that's what it will do. So these would require heat to do that. Okay, and there's some more examples of some decomposition. Single replacement. Remember A, metal, BC, this is B is a metal also, and A replaces B, and B comes out. It's fantastic. You guys are going to do this very reaction right here in the laboratory. You're going to take some copper, you're going to put it into silver nitrate, and boom, you're going to see the silvery stuff come out. It's going to surround the copper bead. And you're going to be like, what is that stuff? It's pure silver. That's what it is. It's pure silver. And the copper is beginning to dissolve. It's going away, and your solution starts to turn blue because copper ions, copper 2+ ions, are blue. And so as the copper is dissolving, your solution's turning blue, and the silver is coming out. Okay? So if you guys had a nice little source of silver nitrate somewhere, you go find it somewhere in the world here. You're like, man, this is a spring of silver nitrate. You put some copper in there, and all the silver would just start coming out of it. Right? So this is one way they want to get all the gold out of the ocean. They want to precipitate all the gold out of the ocean because they're like, well, there's all kinds of gold ions in the ocean. We want to get them out. And so they want to do these single replacement reactions to try to do that. Okay? Maybe that's one of you guys. You're going to figure that out. Okay? Become rich from all the gold in the ocean. Okay, and then finally we have a double replacement reaction. Okay, like I said, the two, they show it a little different way, but basically these two cations switch places. Okay, you could never get BD. Why not? Why could that not ever form? Or AC. Why could those not be products of this reaction? Remember, these are ionic compounds. Why could BD and AC not form? What's the charge of a B? General charge. Is it positive or negative? B is negative. What's the charge of an A? Positive. What's the charge of a C? Positive. D? Why can they not form? You can't have two positives, right? What's going to happen if you take two magnets and they're both positive poles and you try to push them together? They're just going to repel one another. That could never happen. Two negatives, they're going to repel. A positive and a negative, they come together, right? So the only possible products that you can have are the ones that have a positive and negative, positive and negative. Well, I have already one of those over here. So what's the other one? Well, I just simply switch the positives and I'll get the other one. Okay? And now I know the products of this reaction. Those are the products of this reaction. I get AD and BC, or CB, excuse me. So here's a double replacement reaction. You take some lead nitrate. You add some sodium chloride salt, 2 ionic compounds, right? The lead is a positive, the sodium's a positive, the nitrate's a negative, the chlorine's a negative. Whoa, bug. Okay, so these are going to switch places. And then I'm going to get lead chloride as one of my products and sodium nitrate as the other one. Look, the aqueous symbol. That means that these are dissolved. So these two solutions are clear because everything's dissolved. I can't see. They look like water. Just 2 test tubes of water. That's what they look like. You pour them together, and this brilliantly yellow precipitate forms and comes out a solution, lead chloride. Okay? And it comes out as a solid. That's my solid product. The sodium nitrate, it actually doesn't form a solid product. It just remains dissolved. Okay? But we specify it as one of the products because it's a potential product. But it's actually not a product of this reaction because it didn't actually form. It just remained dissolved. I can see that because it's aqueous here, and the sodium and nitrate ions are aqueous here. Okay? Oh. Oops. Jeez. Okay. Okay, so let's see. So slide 47. That's where I went. Okay, we call these double replacement reactions, we call them precipitation reactions. Because that solid lead chloride, that's a precipitate. That's a solid thing that came out of water, out of the water solution. And we call it a precipitate. So these are precipitation. Double replacement reactions are precipitation reactions. Okay? They are precipitation reactions. Now, how will we know if a precipitate will form? Well, we will have this chart. And you will have this as a reference material on your test. Okay? This chart will be a reference material for you. And you just have to know how to read it. So, looking at this chart, can you tell me? Is this a solid precipitate, or does it remain aqueous, which is soluble? Soluble is aqueous. Okay? Insoluble is solid. So, is HgCl2, is it a solid or aqueous? Okay. I hear some people say aqueous. Is everybody in agreement with that? Well, let's look here. Chlorine. Chlorides are what? Soluble. But I need to check the exceptions. What are some of the exceptions to the solubility of chlorine? Is mercury one of them? Sure is. So what does that mean about it?
Insoluble.
It's insoluble. It is not aqueous. It will form a solid product. Okay? So those are the exceptions to this. How about sodium carbonate? Sodium carbonate. Soluble or insoluble? Find carbonate, and you're going to find your answer. CO3 2 minus. Carbonates are what? Well, okay, good. Now check the exceptions. Is sodium an alkaline metal? Sodium's an alkaline metal, right? So, is sodium carbonate aqueous or solid? It's aqueous because it is an exception to the insolubility of carbonates. So, this is a aqueous product. Now, I could have figured out here too. Look, alkaline metals, sodiums are soluble. Are there any exceptions to the solubility of sodium? Not a single one. Not a single one. Okay? So anything with sodium is going to be soluble. All right, we'll pick this up again next time.